Welcome back to the Deep Dive, the show where we take your stack of sources, those fascinating articles, critical research, and invaluable notes, and transform them into crystal clear, actionable insights. Today, we're plunging headfirst into a topic that isn't just evolving, but fundamentally reshaping how software is built, delivered, and even conceived: microservices architecture. You've handed us a wealth of material, asking us to unpack the ins and outs of this architectural paradigm. We'll explore everything from its core principles to its profound market impact and crucial comparisons with older ways of building software. Our mission here for you is to give you that essential shortcut to truly understanding what microservices are, why they've become so dominant, and what their future holds in this ever-accelerating tech landscape.
Indeed, it's a field experiencing truly remarkable growth and widespread adoption across almost every industry imaginable. We'll be meticulously extracting the most important nuggets of knowledge, looking at the underlying reasons why so many companies are making this significant and often challenging shift, and uncovering some surprising facts behind its rapid ascent. Think of this as your express lane to becoming exceptionally well-informed about modern software development practices.
So if you've ever found yourself wondering how digital giants like Netflix manage to stream billions of hours of content seamlessly to millions of users simultaneously, or how Amazon can roll out new features and update its vast marketplace without a single hiccup, often multiple times a day, then you are absolutely in the right place. Let's unpack this fascinating world of microservices. All right, let's kick things off with a fundamental question. We hear the term microservices constantly, and our sources label it the dominant paradigm for modern software development. But what exactly does that mean? What are microservices, really?
Right.
Well, at its core, microservices architecture represents a fundamental philosophical shift in how we approach building complex software. For decades, the dominant model was the monolith, a single, massive, indivisible application where all components were tightly integrated into one code base. Microservices flips that completely on its head. It structures an application as a collection of small, autonomous services, and each of these services is designed around a very specific, narrowly defined business domain or capability.
Okay, so instead of one giant interconnected brain trying to do everything, you're saying it's more like,
Yeah,
like a collection of specialized independent organs, each focusing on a single vital function. That's a perfect analogy, actually, yeah. Imagine an expansive online retail platform. In a monolithic world, every single function, user authentication, product catalog, shopping cart, payment processing, recommendation engine, shipping logistics, all of that would be part of one gargantuan application. With microservices, each of those functions becomes its own self-contained independent service. The user authentication service literally knows nothing about the shipping logistics service beyond, communicating through a defined interface, an API usually. Each of these smaller organs or microservices has its own independent code base. It can be managed by a small, dedicated team, deployed entirely independently of other services, and importantly, scaled up or down based only on its individual requirements.
that sounds incredibly flexible. But why does this specific architectural choice matter so profoundly to us, the end users, or even to a business leader trying to understand the tech driving their company?
The why it matters to you part is transformative. For business, it means that big, complex applications, which often become bottlenecks, slowing down innovation, can be broken down into smaller, far more manageable pieces. This leads to incredibly nimble development cycles. Companies can iterate rapidly, respond to market changes or customer feedback with just unprecedented speed.
So faster features.
Exactly. Imagine your favorite app getting a major new feature, not in months, but maybe in weeks or even days. Furthermore, it results in dramatically more reliable systems because of inherent fault isolation. If a problem arises in, say, that recommendation engine microservice we mentioned, it's highly unlikely to cascade and bring down the entire streaming platform. You might just see, I don't know, a blank recommendation section, but your movie keeps playing.
Right. That's a huge improvement in user experience.
And operational resilience, absolutely.
That makes a lot of sense. It's not just about breaking things down for the sake of it then. There are specific characteristics, almost like a manifesto, that guide this design. What are these core principles that truly define microservices and explain why they're designed this way?
Indeed, yeah, there are several foundational principles, and understanding them is key to grasping its power. The first, and maybe most critical, is independence. Each microservice runs in its own process, often in its own container, and crucially, it manages its own dedicated database. This is foundational. It allows for independent technology choices. One service might use, say, a relational database for structured customer data, while another might opt for a NoSQL document database for rapidly changing product details, whatever is best suited for its specific tasks.
Okay.
This autonomy also extends to deployments and scaling, offering immense efficiency gains.
So they're not all tied to the same underlying database or even the same programming language. That level of flexibility sounds like a complete departure from the past.
It absolutely is, and it leads directly to the second principle, technology diversity, sometimes called polyglot persistence or polyglot programming.
Mhm.
Because services are independent, different teams can choose different programming languages, databases, frameworks, tools, whatever is best suited for their specific microservices tasks.
Wow.
This boosts flexibility, efficiency, and lets teams leverage the most appropriate, sometimes cutting-edge technologies. Next, microservices are inherently business-focused. Unlike traditional architectures where you might organize components by technical layers, like a database layer or UI layer, microservices are organized around specific business capabilities. So you have a user management service, a payment processing service, a product inventory service.
Okay.
This makes the whole system more intuitive to understand, to align with business goals, and just easier to maintain as it directly mirrors how the business actually operates.
And I imagine this organizational alignment and independence also helps speed up decision-making, cutting through some of the usual bureaucracy.
It does, yeah. This is where decentralization comes in. Decision-making authority and data management are distributed throughout the system, down to the individual teams owning their services. This fosters faster innovation cycles because small, autonomous teams can make decisions quickly about their own service without needing central approval or navigating those large bureaucratic bottlenecks. And crucially, we have fault isolation. This is a major differentiator. Because services are independent, failures in one service are far less likely to cascade and impact the entire system.
Right, the streaming example.
Exactly. We touched on that earlier, but think about any critical online service. If a minor non-essential feature glitches, the entire application doesn't just grind to a halt. This significantly improves overall system resilience and ultimately the user experience.
This all sounds incredibly compelling. And is this just theoretical, though, or are we truly seeing this widespread in the market across different industries?
Oh, it's definitely not just theory or some niche trend. It's become an undeniable strategic imperative for modern enterprises across the globe. The global microservices market itself is experiencing remarkable growth. Our sources say it was valued at what? USD 4.2 billion in 2024, and it's projected to soar to an astonishing USD 13.1 billion by 2033. That's an impressive compound annual growth rate, a CAGR of 12.7%.
Huge growth.
But here's the truly striking figure, the one that really shows its mainstream adoption. As of 2024, an astonishing 85% of modern enterprise companies are actively managing complex applications using microservices.
85%. Wow.
Yeah. So for you, the listener, whether you're a business leader or just a tech-savvy consumer, this widespread adoption has direct implications. The applications and services you rely on every single day, your banking app, your favorite streaming platform, your online shopping experience, they're increasingly powered by this architectural style. And this directly translates to the faster updates you see, the more personalized experiences because components can be tailored more easily. It's truly everywhere.
It's clear that microservices are a huge deal today, really the backbone of so many modern digital experiences. But how did we actually get here? This didn't just appear out of nowhere, right, as some sudden revelation. I heard the term service-oriented architecture, SOA, mentioned in the past. How do microservices fit into that broader evolution of software design?
You're absolutely right. The concept didn't appear in a vacuum. Microservices certainly evolved from service-oriented architecture, SOA, which predates it significantly. The idea of breaking down larger systems into smaller, reusable services has been around for quite a while. But the distinct concept of microservices, as we understand it today, really started gaining significant momentum around, say, 2014. Martin Fowler, a highly influential software developer and author, is widely credited with promoting the idea, taking those often larger, more comprehensive SOA services, and further breaking them down into the more granular, focused, and truly independent microservices we see dominating today.
So it's not just a completely new invention, but maybe a refinement. A more extreme or purist version of SOA, perhaps? What's the key distinction that makes it so fundamentally different? And why did it gain traction over traditional SOA?
That's a crucial distinction for you to grasp, yeah, because it explains why the shift occurred. SOA often involved larger, more comprehensive services that might still share central components and typically a centralized enterprise service bus, or ESB, for communication.
All right, the ESB, I remember those.
Yeah, and that ESB often became a single point of failure and a bottleneck. Plus, the services, while separate, could still suffer from tight coupling due to shared schemas or centralized governance. Microservices, on the other hand, emphatically emphasize smaller, focused services. They use direct, lightweight communication between them, often simple HTTP REST calls or asynchronous message queues, and critically, decentralized governance. Each microservice team effectively owns its service end-to-end, including its data model and technology stack. This significantly reduces reliance on central orchestrators and minimizes coupling. It's less about a shared bus, more about independent peer-to-peer communication.
That decentralization, that independence, seems to be the driving force behind a lot of the benefits we discussed earlier. What specific technological leaps really fueled this shift away from traditional SOA towards the microservices model we recognize now?
Right. The timing of microservices' ascent wasn't accidental. It was really enabled by several concurrent and powerful technological advancements. These were the driving forces. The first, and arguably most pivotal, was containerization, championed by tools like Docker.
Docker, okay.
Before Docker, deploying applications meant worrying about OS versions, libraries, dependencies, often leading to that infamous "it works on my machine" problem.
Oh yeah, I've been there.
We all have. Containers provided lightweight, portable runtime environments that could encapsulate an entire service with all its dependencies. This ensures consistent execution across any environment, from a developer's laptop right through to production servers. It just made it far easier and more reliable to package and run multiple independent services.
So packaging them up into these neat self-contained boxes made them much easier to move around, deploy, manage at scale.
Exactly. It dramatically simplified the deployment pipeline for independent services. Then you have the pervasive rise of cloud computing. Cloud providers like AWS, Azure, Google Cloud, they provided elastic on-demand infrastructure. This meant companies could scale compute and storage resources up and down dynamically as needed, paying only for what they use.
So years ago.
Precisely. And this perfectly complements the independent scaling needs of microservices. Individual services can consume resources based on their specific demand, rather than needing to over-provision an entire monolithic application. Next, DevOps practices played a massive symbiotic role. The cultural and technical shift towards DevOps facilitated continuous integration, CI, and continuous deployment, CD. Automated CI/CD pipelines dramatically shortened development cycles, making the rapid, independent deployments of microservices not just a theoretical benefit, but a practical, everyday reality.
Right, you couldn't manage thousands of manual deployments.
Absolutely impossible. It would be a nightmare. And finally, API-first design became the standard. This approach emphasized designing and building well-defined, stable interfaces APIs for seamless service-to-service communication before implementation. This promoted loose coupling and clearer contracts between services, which is absolutely vital for a distributed microservices architecture to function effectively.
It sounds like a perfect storm of technological innovation, where each advancement sort of synergistically supported the rise of microservices. Were there specific moments or maybe flagship companies whose adoption really solidified microservices as the go-to approach, really showcased its power?
Absolutely. The timeline is quite clear, marked by key milestones and early adopters. In 2014, Google introduced Kubernetes. This open-source platform quickly became the dominant container orchestration platform.
Kubernetes, yeah, you hear that everywhere now.
Essential for managing hundreds or thousands of containerized microservices at scale. It automated the complex dance of deployment, scaling, service discovery, self-healing, basically everything for distributed applications. Its introduction was a massive game changer for large-scale microservices adoption. Following that, between roughly 2015 and 2016, major tech giants like Amazon, Uber, and Spotify widely adopted microservices. They showcased its efficacy for high-scale, agile development in incredibly demanding environments. Their success stories provided tangible proof that microservices weren't just a good idea on paper, but a proven, effective strategy for building resilient, highly scalable systems in the real world.
So these are the early adopters, the trailblazers, who really put microservices on the map for the broader industry.
Precisely. And their documented successes paved the way for broader enterprise adoption. By 2018, our sources show a significant 63% of enterprises reported adopting microservices, indicating a clear and accelerating industry shift away from monolithic systems. Fast forward to today, 2024, and that widespread adoption has solidified, hitting that 85% mark of modern enterprise companies we mentioned. This cements its status not just as a trend, but as the mainstream standard approach for building robust, scalable enterprise software.
When we talk about these early success stories and the true scale of microservices, the one name that always seems to come up is Netflix. How did they specifically leverage microservices to achieve the global scale and agility they're known for?
Netflix is arguably the definitive prime example, yeah. A textbook case of successful microservices transformation. They famously rebuilt their entire architecture from the ground up, moving from their original monolithic DVD by mail service into the global streaming platform we know today, powered entirely by microservices.
Must be a huge number of services.
It's truly colossal. They literally operate over 1,300 distinct microservices. These collectively handle billions, literally billions, of requests daily.
Right.
Think about it: recommending content, transcoding video, streaming in different formats, managing user profiles, processing payments globally, handling all the complex infrastructure, A/B testing new features. Each of these functions is a dedicated, independent microservice. This enabled what they themselves describe as unprecedented scalability and rapid feature deployment. This is precisely why Netflix can handle hundreds of millions of concurrent users without a hiccup, and why they can rapidly introduce new features, roll out support for new languages, adapt to global demands, integrate with new devices seemingly overnight.
Incredible agility.
Their story is a powerful testament to the agility, resilience, and sheer operational scale that microservices can provide. It's really a masterclass in managing extreme complexity through modularity.
So we've thoroughly covered the what and the why of microservices and how they came to dominate the software landscape. Now, let's peel back the layers a bit and peek under the hood. For someone who wants to understand the nuts and bolts, what are the essential technical components that truly make this distributed system work? And what are the strategic patterns companies use to actually implement them effectively?
Excellent question. Because building a microservices architecture isn't simply chopping a large application into smaller pieces. It really requires a sophisticated ecosystem of specific tools and architectural components to manage that inherent complexity of a distributed system. At the very heart of it, of course, are the microservices themselves. These are the individual, self-contained units we've been discussing, each embodying its own unique business logic, managing its own data access, and exposing its API endpoints for communication. They are typically designed to be stateless where possible, meaning they don't hold session-specific data between requests. That's crucial for making them easier to scale horizontally.
Okay, so these are like little independent workers, each highly skilled in one specific task. But if I, as an external client, say, my smartphone app, want to interact with this vast web of hundreds, maybe thousands of these services, how do I even find the right one? There must be some kind of central coordinator or traffic director, right?
You've hit on a crucial component, the API gateway. This acts as the single unified entry point for all client requests into your microservices ecosystem. Think of it as the ultimate traffic cop and maybe bouncer rolled into one.
Okay.
It handles routing incoming requests to the correct microservice, manages user authentication and authorization, applies rate limiting to prevent abuse, performs load balancing to distribute traffic efficiently across multiple instances of a service. Critically, it simplifies how external systems interact with what is internally a very complex and dynamic web of services. It insulates clients from that underlying complexity.
Got it. Examples might be.
Oh, things like Netflix Zool, Spring Cloud Gateway, or even NGINX configured appropriately.
That simplifies things for the external world. But once a request gets past the gateway and one microservice needs to talk to another internally, how do they find each other? Their addresses must be constantly changing as services scale up and down, right?
Precisely. That's where the service registry and discovery pattern comes into play. This is essentially a constantly updated directory or a phone book for your services. When a microservice starts up, it registers itself with the service registry, saying, here I am at this address. When another service needs to communicate with it, instead of having a hard-coded address, it queries the registry to find out where the desired service is currently running.
Dynamic lookup.
Exactly. This enables dynamic communication and makes the system resilient to changes in service locations or scaling events. Popular tools for this include HashiCorp Console, Netflix Eureka, or the native service discovery capabilities built directly into Kubernetes itself.
And we discussed containerization earlier as a major enabler. That sounds like it's fundamental to how these individual services are actually packaged and run.
Absolutely. Container technologies, primarily Docker, are foundational here. They provide those lightweight portable runtime environments we talked about. They encapsulate an application service along with all its dependencies, libraries, configurations, even OS specifics into a single isolated package.
The box.
The box, exactly. This ensures consistency. A service runs exactly the same way, whether it's on a developer's machine, a testing server, or in production. Finally solving that "it works on my machine" headache. And because you'll have many, many containers running numerous microservices, you need a robust way to manage them all. This is where container orchestration platforms become essential.
Like Kubernetes.
Kubernetes is the dominant platform here, yeah. It essentially serves as the operating system for your distributed microservices application at scale. It automates deployment, handles scaling services up or down based on demand, provides self-healing by automatically restarting or replacing failed containers, offers built-in service discovery and load balancing. It truly manages the entire lifecycle of your containerized services.
So Kubernetes orchestrates the entire fleet of these little microservices. Once they're running and they've found each other through the service registry, how do the services actually communicate? What's the language they speak between themselves?
Right, that brings us to inter-service communication. There are a few primary ways services talk to each other, each suited for different scenarios. For synchronous, request-response calls, where one service needs an immediate answer from another, like asking a user management service for user details, HTTPS is still very common.
Simple and standard.
Easy to implement, widely understood. For high-performance, lower latency communication, especially in high-volume scenarios or when dealing with mobile clients, gRPC is often used. That stands for Google Remote Procedure Calls. It's built on HTTP2 and uses protocol buffers for efficient data serialization.
Faster, more efficient.
Generally, yes. And then for asynchronous, event-driven communication, where services don't need an immediate response but react to events, like a new order being placed, which triggers updates in inventory, shipping, payment services, etc. Message brokers like Apache Kafka or RabbitMQ are crucial.
Kafka, RabbitMQ, okay.
This promotes loose coupling. Services can operate even if a dependent service is temporarily unavailable, as messages can be queued and processed later. Very resilient.
Now, what about data? We've heard that each service is independent, can even use its own tech stack. Does that mean each service also has its own dedicated database? That sounds like it could lead to significant data consistency challenges.
You're perceptive. It absolutely does. The database per service pattern is indeed a core best practice in microservices architecture. Each microservice maintains its own dedicated database. This is fundamental for preventing data coupling between services and enabling the independent evolution of each service's data model without impacting others. It grants incredible flexibility and autonomy. But, as you noted, it absolutely introduces complex challenges around distributed data consistency. You can't just run a traditional A/D transaction atomicity, consistency, isolation, durability across two different services databases as easily as you would within a monolith.
Right.
We'll definitely touch on sophisticated solutions like the Saga pattern and event sourcing later when we discuss challenges. They're key to addressing those consistency issues.
That pattern makes sense for autonomy, but clearly requires careful handling. So with all these technical pieces, how do companies actually go about breaking down their existing large applications into microservices or designing new ones from scratch? Are there specific strategies or patterns they follow to manage this decomposition effectively?
Yes, definitely. There are several strategic implementation patterns that guide this decomposition, moving beyond just the raw technical components. One of the most important is domain-driven design, DDD. This isn't just a technical pattern. It's a powerful software development approach that focuses on aligning service boundaries with specific business domains and their bounded contexts.
Bounded context. What does that mean?
It means identifying distinct business areas where terms and concepts have a consistent, specific meaning. For example, customer in a sales context might have different attributes and behaviors than customer in a support context. Those are different bounded contexts. By designing services around these natural business divisions, you ensure the services are intuitive, cohesive, and truly represent a singular business capability. This makes them more maintainable and resilient to change over time.
So instead of breaking it down by technical layers, like a data layer service, a business logic layer service, you literally break it down by business functions, like order processing or user profile management.
Precisely. It keeps the services truly focused on a business capability and prevents them from becoming sort of mini monoliths themselves. Now, for companies that have existing large monolithic applications, attempting a big bang rewrite, where you stop development on the old system and try to build an entirely new microservices system all at once, is incredibly risky.
Yeah, that sounds dangerous.
Often leads to project failure. That's where the strangler fig pattern comes in as a powerful incremental migration strategy.
The strangler fig pattern, that sounds organic. What is it and why is it so effective?
It's named after the strangler fig tree, which starts as a vine on a host tree, slowly grows around it, eventually overshadowing and replacing the host. In software, instead of that risky Big Bang rewrite, new microservices are gradually introduced to handle specific functionalities that are peeled off from the existing monolithic system. As new microservices are built and proven, traffic for that specific functionality is rerouted to the new service, often via that API gateway or a proxy.
Oh, okay. Little by little.
Exactly. Over time, these new microservices strangle or replace more and more functionality from the existing monolith. This minimizes risk during migration, allowing for a phased, safer transition where the old and new systems coexist for a period. You learn iteratively, manage risk, and continuously deliver value while gradually dismantling the monolith piece by piece. It's a much more pragmatic and proven approach for transformation.
This is truly a fascinating architecture, and we're starting to see why companies are so keen on it, especially with that strangler fig pattern, making migration seem less daunting. Let's shift our focus now to the real-world impact. Beyond the technical elegance, what are the actual business benefits and the undeniable market momentum driving this widespread adoption we talked about earlier?
Yeah, the market data here really speaks volumes, and it underscores the strategic importance of microservices. As we mentioned, the global microservices market is not just growing, it's booming, projected to reach USD 13.1 billion by 2033 from its 2024 valuation. And if we zoom in specifically on the cloud microservices segment, that alone is projected to hit USD 8.06 billion by 2032.
So it's a huge market.
It is. This
Right.
isn't just about general software growth. It's a clear, powerful indicator of sustained, substantial investment and confidence in this architectural style across the enterprise world.
So it's not just a passing trend. It's a significant established segment of the tech industry, almost a foundational pillar now. Who are the key players in this ecosystem that facilitate this transformation?
Right, you have a whole ecosystem of critical players that make microservices viable at scale. The major cloud providers, AWS, Microsoft Azure, Google Cloud Platform, GCP, they're absolutely fundamental, offering the elastic, on-demand infrastructure and a plethora of managed services that microservices thrive on.
Type cloud platforms.
Then there are the foundational container and orchestration vendors like Docker and Kubernetes, which are the absolute core tools for packaging, deploying, and managing these services. Beyond that, you have service mesh providers such as Istio and Kong. They simplify inter-service communication, add crucial layers of security like mutual TLS, and enhance observability.
Istio, Kong,
Yeah.
service meshes.
Got it. And finally, robust monitoring and observability solutions like Datadog, New Relic, Dynatrace. They are crucial for keeping tabs on these incredibly complex distributed systems. They allow teams to quickly identify and resolve issues. You need that visibility.
So it's a complete mature ecosystem supporting this architecture, which helps explain its rapid adoption. Can you give us some specific real-world examples of how different industries are actually leveraging microservices to gain a competitive edge?
Absolutely. Let's start with e-commerce and retail, with giants like Amazon and Netflix leading the charge. They leverage microservices for what our sources call unprecedented scalability during massive traffic spikes.
Like Black Friday?
Exactly. Think about the sheer volume of transactions and concurrent users on Black Friday, Cyber Monday, or the global launch of a new, highly anticipated show on Netflix. Microservices allow them to scale individual components like payment processing, product browsing, video streaming independently, rather than having to scale their entire system, which would be incredibly inefficient and costly. This also enables rapid feature deployment, allowing them to roll out new features, updates, and adapt quickly to market demands, sometimes multiple times a day.
That makes perfect sense for high-volume, dynamic environments like retail. What about industries that might seem more conservative, like financial services? where security and reliability are paramount.
Even in seemingly more conservative sectors, microservices are making a huge impact. In financial services, they are crucial for building secure, compliant applications that can scale individual components based on transaction volumes. This is incredibly important for banks, trading platforms, digital payment systems that experience wildly fluctuating loads throughout the day.
Like month-end processing or market open.
Precisely. Think end-of-month payroll processing or peak trading hours. Our sources indicate that digital payment platforms built on microservices show 60% better scalability. That's essential for securely and efficiently handling vast numbers of transactions, while also meeting stringent regulatory demands and ensuring continuous availability. And then there's healthcare, another highly regulated and sensitive industry. Here, microservices ensure reliable access to patient data while maintaining stringent security and compliance requirements. Modular electronic health records, EHR systems, and sophisticated telemedicine platforms greatly benefit from the flexibility and resilience of microservices.
So they can update parts without taking the whole patient record system offline.
Exactly. It allows for secure, adaptable systems that are absolutely vital for modern patient care and data management. You can rapidly integrate new medical devices or compliance updates without re-architecting an entire system.
Those are powerful, diverse examples. But ultimately, for a business, it comes down to the bottom line, doesn't it? What's the tangible return on investment? Are there quantifiable business benefits that truly highlight why companies are making this significant and often costly architectural shift?
This is where the numbers truly tell the story, yeah? And they are very concrete. The benefits aren't just qualitative, they translate into significant competitive advantages. For development productivity, companies report a staggering 53% faster time to market for new features.
53% faster, that's huge.
It means new capabilities, new products, critical updates get into your hands, the user, or your customer's hands much, much faster. It's also linked to a 41% increase in overall development productivity, meaning teams can simply get more done. This isn't just about efficiency, it's about building an organization that inherently learns and adapts faster than its competition, transforming technology from a cost center into a core innovation engine.
And I've heard rumors that high-performing teams leveraging microservices deploy much more frequently. Is that really a significant factor?
It's more than true. It's a defining characteristic. Our sources show that high-performing teams achieve 208x more frequent deployments compared to their traditional counterparts.
208 times.
Imagine releasing updates hundreds of times more often than your competitors. The speed directly translates to a massive competitive advantage, enabling constant iteration and responsiveness to market signals. For operational efficiency, despite the initial investment, we see a 35% reduction in long-term development costs because of the modularity and reduced coupling. And for system reliability, there's a 45% improvement in application resilience. That means less downtime, fewer outages, and a consistently more reliable service for you, the end user.
Better uptime.
Exactly. Finally, for team collaboration, a remarkable 84% improved collaboration between team members is reported. When teams own their services end-to-end, they work more efficiently, more autonomously, fostering a deep sense of responsibility and accelerating innovation.
Wow, so it's not just about the tech itself, it's profoundly impacting the people, the processes, and ultimately the entire business strategy.
Absolutely. The big picture here is that these benefits translate directly into profound competitive advantages. Microservices allow organizations to innovate faster, scale more effectively, deliver more reliable and available services, ultimately leading to better user experiences, increased customer satisfaction, and often market dominance. It's about building a robust, adaptable, and continuously evolving engine for sustained business growth and just staying ahead in a dynamic digital world.
That's a powerful and persuasive case for microservices, but it's crucial to remember, as you said, it's not the only way to build software. For a long time, and still in many contexts, monolithic architecture was and is the standard. So for an organization considering its next steps, how do they weigh the options? What are the key trade-offs when we compare microservices to the traditional monolithic approach?
This is an absolutely critical discussion, because microservices are not a universal panacea. They're not right for everyone or every situation. Understanding where and when microservices fit requires a clear-eyed look at the alternatives. Let's start with monolithic architecture, the traditional approach. The entire application is built as a single, indivisible unit. All components, UI, business logic, Data access layers tightly integrated into a single code base, typically sharing a single database.
One big block of code.
Pretty much. Think of it as a single, massive, executable, or application archive that gets deployed as a whole unit.
So like one huge self-contained software package that does everything. What were or are the advantages of that traditional approach? Why did we do it that way for so long?
Well, for small teams, simple applications, or when you're just starting out, monoliths still offer significant advantages. They are generally simpler to develop and debug, especially early on. All the code is in one place. You're working within a single development environment.
Easier to get going.
Definitely. There's no network latency for internal calls, so communication between components within the monolith is extremely fast, operating in memory. Testing can be easier as it often involves testing just a single deployment unit. And crucially, the base infrastructure costs can be lower initially since you're running just one large application rather than needing sophisticated orchestration for many small ones.
Okay, so straightforward, potentially faster to get started, and initially cheaper. But we know microservices offer something very different, particularly as things grow. What are their direct advantages in contrast to that monolithic simplicity?
Right. In direct contrast, microservices offer several compelling advantages, particularly as systems grow in complexity and scale. They provide superior scalability. Individual services can scale independently based on demand rather than having to replicate the entire huge application. They enable that technology diversity we mentioned, pick the best language, framework, or database for each specific job, optimize locally, huge flexibility. This fosters incredible team autonomy. Small, dedicated teams can develop, deploy, and operate their services without needing constant, deep coordination with other teams. That accelerates development. You also get robust fault isolation. A bug or failure in one service is significantly less likely to bring down the entire system. And finally, significantly increased innovation speed, because features can be developed, tested, and deployed in parallel by different teams, dramatically shortening release cycles.
That sounds like a fundamental trade-off.
Mm.
Simplicity and potentially raw internal speed on one hand versus flexibility, resilience, and scale on the other.
Yeah.
But what about that performance point? You mentioned network latency. If microservices are communicating over a network, doesn't that inherently introduce delays compared to those fast in-memory calls within a monolith?
You've hit on a critical and often cited trade-off. Yes. Our sources consistently indicate that microservices typically observe 2-3x higher response times compared to monolithic systems for equivalent operations.
2 to 3 times slower.
For that specific interaction, potentially, yes. This is indeed due to the unavoidable network overhead involved in inter-service communication. Services are no longer calling functions directly in memory, they're communicating across a network. It's a fundamental architectural trade-off organizations must consciously accept and design around. However, and this is the crucial part, here's where the strategic advantage emerges. While individual service calls might be slightly slower, microservices achieve 208x more frequent deployments and 106x faster lead times.
Ah, so much faster delivery of new stuff.
Exactly. The overall system can evolve, adapt, and deliver new features to you, the user, dramatically faster. It's a strategic trade-off. Raw internal transaction speed versus agility, continuous delivery, and overall business responsiveness. It's about optimizing for the pace of innovation rather than just the raw speed of a single internal function call.
That's a fascinating exchange of capabilities. So given these inherent trade-offs, how does an organization decide which architectural path to take? Is there a clear decision framework for when to choose one over the other?
Absolutely. It's not a one-size-fits-all situation. There's a pretty clear framework for making this strategic decision. You should generally choose a monolithic architecture when you have a relatively small development team, say fewer than 10 developers. If your DevOps expertise is limited or just nascent. If you're building a relatively simple application with well-understood requirements that aren't expected to change drastically.
Keep it simple.
Yeah. Monoliths are also often the preferred choice for building an MVP, a minimum viable product to get something out quickly to market and validate an idea. And finally, if you have very strict initial cost constraints, as the infrastructure and operational overhead for monoliths are typically lower upfront.
So small team, simple app, tight budget, or just getting started lean towards the monolith makes sense. When does microservices become the clear, compelling choice then?
You should unequivocally choose microservices when your application complexity is high and growing, meaning it's becoming large, unwieldy, difficult to manage as a single unit.
Feeling the pain of the monolith
Exactly. This is often the case when you see performance bottlenecks, deployments become slow and risky, or you struggle to scale specific parts of your application. It's ideal if you have varying scalability requirements for different parts of the application, like our video streaming example, where content delivery needs to scale way more rapidly than user authentication. If you have multiple independent teams that need to work in parallel on different parts of the system, this architecture enables that autonomy. If you already have a strong, mature DevOps culture in place with robust automation and continuous delivery practices, microservices will truly flourish there. And finally, if you need very high availability and resilience where the failure of one component simply cannot impact the entire system, microservices provide that crucial fault isolation. Certain industries are particularly well suited for microservices due to their inherent needs. E-commerce, where traffic spikes are common and rapid feature rollout is critical. Financial services, due to fluctuating transaction loads, stringent compliance needs, and the demand for extreme security and reliability. And media and entertainment, for managing vast content libraries and streaming to millions globally. These sectors greatly benefit from the ability to handle variable loads, meet compliance requirements, and satisfy the sheer demand for innovation speed that microservices can unlock.
We've painted a pretty compelling picture of the benefits and the strategic rationale behind microservices. But it's crucial we're entirely honest about the journey. Microservices aren't a silver bullet, right? They introduce their own unique and significant complexities. What are some of the inherent challenges of moving to or managing these distributed systems?
You're absolutely right. The significant benefits we've discussed come hand in hand with a considerable increase in inherent complexity, particularly at the operational level. The biggest challenge often cited is operational complexity. Managing numerous independent services requires sophisticated tooling and processes for service communication, routing, dynamic discovery.
Keeping track of everything.
Exactly. Imagine trying to coordinate hundreds of small independent teams, each building their own piece of a vast puzzle without a robust automated system to help them communicate and know where everyone else is. This leads directly into the next challenge: monitoring and observability. Traditional monitoring tools designed for monolithic applications are simply insufficient in this landscape. You need sophisticated distributed tracing to follow a request as it hops across multiple services. You need centralized logging to aggregate logs from hundreds of different sources, and comprehensive metrics collection for every single service to truly understand what's happening across this vast web of interconnected components.
So you can actually debug things.
Trying to debug an issue without these tools is like trying to find a needle in a haystack in the dark, wearing a blindfold. It's incredibly difficult.
So it's not just about building the individual services, but also about building and maintaining the sophisticated infrastructure and tools to manage those services and understand their interactions. What about getting updates and new features out once you have so many independent pieces? That sounds complex too.
Precisely. Deployment and release management also become significantly more challenging. You face issues like service versioning. How do you ensure Service A can still talk to Service B if Service B updates its API in a breaking way? You need to carefully coordinate rolling updates across many interdependent services to ensure continuous availability. Managing dependencies between services becomes a finely choreographed dance, often requiring complex automation and strategies like canary releases or blue-green deployments. It's a continuous, complex orchestration.
Okay, so a lot of operational overhead. What about the core technical hurdles within the services themselves? We touched on the database per service pattern earlier, which sounded like it could create some interesting data issues.
Indeed. One of the biggest technical hurdles is data management and consistency. When each service owns its own dedicated database, ensuring data consistency across multiple independent services becomes incredibly complex. You cannot simply run a traditional ACID transaction. Atomicity, consistency, isolation, durability, which guarantees immediate consistency across two separate databases owned by different services. That just doesn't work easily.
So you can't guarantee everything updates perfectly all at once.
Not in the same way you could in a monolith, no. This requires a shift in mindset and new approaches, often embracing what's called eventual consistency.
So how do companies solve that without sacrificing data integrity? What's eventual consistency?
There are several sophisticated solutions and patterns that lean into eventual consistency, meaning the system becomes consistent over time, though not necessarily instantaneously. Patterns like the Saga pattern come into play. This manages distributed transactions as a sequence of local transactions. Each step updates a single service's database. If any step in the sequence fails, compensating actions are triggered automatically to unwind or roll back the previous successful transactions, ensuring overall consistency eventually.
Like an undo for each step.
Exactly. Imagine booking a complex trip flights, hotel, rental car. Each is a separate service. If the car booking fails, a saga ensures the system can automatically unwind and cancel the flight and hotel bookings, maintaining consistency across those multiple independent services. Another approach is event sourcing, which involves storing all changes to application state as a sequence of immutable events, like a log of everything that happened. This provides a complete auditable history and can support various read models tailored for different needs. And CQRS, Command Query Responsibility Segregation, separates read and write operations, allowing for optimized data models for different access patterns, which often leads to better performance and scalability, particularly for reads. Another significant technical hurdle is network reliability and latency. As we discussed, the increased response times, typically 2-3x higher, are due to that network overhead. Services are communicating over potentially unreliable networks, not calling functions directly in memory. Things can go wrong.
And how do they make sure that network communication is resilient and reliable,
Yeah.
even if things inevitably go wrong in distributed systems?
They implement robust resilience patterns. Think of tools like the circuit breaker pattern. Much like an electrical circuit breaker, it stops calls to a failing service after a certain threshold of failures. This prevents cascading failures throughout the system. It breaks the circuit temporarily to protect other services.
Stops hammering a service that's already down.
Exactly. Then there's retry with exponential backoff. This pattern retries failed calls, but with increasing delays between retries, giving the failing service time to recover without overwhelming it. And the bulkhead pattern isolates resources for different services or calls, preventing a failure in one area from taking down the whole system, much like the watertight compartments in a ship's hull, limits the blast radius.
That makes a lot of sense, building in those safeguards. What about security? More services means more API endpoints. It sounds like a much larger attack surface.
Absolutely. Microservices inherently introduce an expanded security surface, more API endpoints, more inter-service communication paths, more deployment units, inherently mean more potential vulnerabilities that attackers could exploit. Common API threats identified by groups like OWASP include things like broken object level authorization, where access controls are poorly implemented for individual resources, allowing unauthorized access. Injection attacks, like SQL injection, which can now target many more distinct endpoints. And excessive data exposure, where APIs return more data than necessary to the client, leading to potential data leaks if intercepted.
So how do organizations secure this significantly expanded attack surface without becoming overwhelmed?
Solutions need to be comprehensive and ideally automated. They include service mesh security, often leveraging MTLS, mutual TLS, for secure, encrypted, and authenticated service-to-service communication within the mesh. This ensures only trusted services can talk to each other.
Encrypting internal traffic.
Yes. Network segmentation isolates services into distinct network zones, limiting the blast radius if one service is compromised. Secrets management centralizes the secure handling of sensitive credentials like API keys and database passwords, rather than scattering them in config files. And runtime security continually monitors service behavior for anomalies or attacks in real time. Security becomes an integrated, continuous process, not just an afterthought tacked on at the end.
This all sounds like it also requires significant changes in how teams work and are structured. What are the organizational challenges that often emerge during a microservices transformation?
That's a critical point, yeah, and it often proves to be the hardest part of the journey because it ties directly back to Conway's Law.
Conway's Law, remind us.
This law basically states that organizations design systems that mirror their communication structures. Microservices, therefore, essentially require organizational changes to align team structures with service boundaries. You need to move away from traditional, often siloed, functional teams like a separate UI team, API team, database team, towards autonomous, cross-functional teams that own a specific business service end-to-end. The whole you build it, you run it philosophy.
Big cultural shift.
Huge cultural and structural shift. Moving from a command and control model to one of empowered, independent teams. And of course, this transformation inevitably creates skills and knowledge gaps. It requires significant expertise in distributed systems design, containerization, cloud-native technologies, advanced observability tools, stuff that wasn't necessarily common before. This means a substantial and sustained investment in training and skill development for existing teams or hiring new talent.
So it's not just a technical problem. It's profoundly a people and culture problem, too. Given all these complexities, what are the best practices for mitigating these challenges and ensuring a successful microservices adoption?
There are several proven strategies that organizations have found to be crucial. First, incremental adoption. Cannot stress this enough. Instead of attempting a risky, big bang rewrite of your entire system at once, adopt microservices incrementally. Start small. Maybe extract a non-critical service from an existing monolith using the Strangler fig pattern. Learn iteratively, validate your assumptions on a smaller scale.
Don't bite off more than you can chew.
Exactly. Second, automation first. This is non-negotiable. Heavy, consistent investment in CI/CD pipelines, infrastructure as code tools like Terraform or CloudFormation, monitoring automation. If you're managing hundreds of services, you simply cannot do it manually. It's humanly impossible and incredibly error-prone.
Automation sounds like the absolute key to handling the sheer scale and complexity.
It absolutely is. Third, observability investment. Prioritize comprehensive observability, distributed tracing, centralized logging from day one. You need to be able to see exactly what's happening across your distributed system at all times. Without it, debugging becomes a nightmare. Fourth, leadership commitment. This transformation is long-term and complex. It requires sustained leadership support for the significant investment in tooling, the necessary team transformation, and that profound cultural shift Conway's Law demands.
Exactly from the top.
It's a strategic business decision, not just an IT project. Finally, governance and standards. While promoting team autonomy, it's crucial to establish clear API standards, security policies, and operational standards. This ensures consistency, interoperability, and security across the organization without stifling individual team innovation. Provides guardrails, not roadblocks.
So we've covered where microservices came from, how they work, and the formidable challenges they bring. But technology never stands still, does it? It's constantly evolving. What's on the horizon for microservices? How is this landscape continuing to evolve, and what new innovations should we be looking out for?
You're right, the microservices landscape is incredibly dynamic and continually evolving, driven by advances in cloud-native technologies, the increasing role of AI, and just ever-changing business needs for speed and efficiency. It's a very exciting space to watch.
What are some of the key future trends that you see shaping how microservices are built and operated?
One of the most significant is the accelerated evolution of event-driven architecture, EDA. While we've discussed message brokers, EDA is becoming even more central for building responsive and dynamic systems, allowing services to react in real time to events rather than relying solely on synchronous requests.
Reacting to things happening instead of being asked.
Exactly. This is particularly valuable for industries like e-commerce for real-time inventory updates during flash sales, banking for instant fraud detection, or IoT for immediate processing of sensor data. It allows for highly decoupled, scalable, and resilient systems. Another major trend is the increasing adoption and maturation of serverless computing. Think AWS Lambda, Azure Functions, Google Cloud Functions. This offers fine-grained scaling, reduced operational overhead, and significant cost optimization by allowing developers to run individual functions or small services without having to provision or manage any underlying servers.
Just run the code.
You only pay for the exact compute time your function is actively running. The serverless market is projected to reach an impressive $21.1 billion by 2025. That underscores its growing significance and its powerful synergy with the microservices paradigm, allowing for even smaller, more ephemeral services, sometimes called nanoservices, or just functions.
So even less infrastructure to manage directly. And what about the physical location where these services run? Is everything still just in the big cloud data centers?
That brings us to edge computing convergence. As demand for extremely low latency applications grows, especially for real-time processing, think IoT devices collecting data in a smart factory, 5G telecom networks handling massive data streams, or real-time patient monitoring in healthcare. Edge computing becomes key. This paradigm enables computation and data processing to happen much closer to the data source, minimizing network delays and bandwidth usage.
Processing closer to the user or device.
Exactly. Microservices, with their small footprint and independent deployment capabilities, are a natural and ideal fit for being deployed at the edge, allowing for distributed intelligence closer to where it's needed.
It seems like AI is becoming an integral part of almost every aspect of technology these days.
Right.
How does that factor into the future of microservices?
You're spot on. AML integration is increasingly important and will likely revolutionize microservices operations. AI will increasingly be integrated into microservices for automated operations, intelligent resource management, predictive analytics.
Like the system managing itself.
To a degree, yes. Imagine systems that can automatically detect anomalies and self-heal, predict traffic spikes, and scale themselves proactively before any human intervention is needed, or intelligently route requests based on real-time performance data. This shifts operations from reactive troubleshooting to more proactive, intelligent management, AI ops, they call it. We also expect continued service mesh maturation. While service meshes like Istio are already powerful, they are becoming lighter and more efficient, with even more enhanced features for observability, sophisticated traffic management patterns, and robust security. This will make them even more pervasive and less resource-intensive to operate. And finally, there's a strong push for standardization across the microservices ecosystem. Industry efforts like OpenTelemetry for unified observability and the Service Mesh Interface, SMI, are working to standardize patterns, APIs, and interoperability across different vendors and tools.
Making things work together better.
Exactly. Reducing vendor lock-in and making the ecosystem more cohesive and easier to navigate for enterprises.
So all these trends seem to be making microservices even more powerful, more efficient, and potentially easier to manage in the long run. What are the long-term strategic implications of all this evolution for organizations?
The long-term strategic implications are truly profound and extend far beyond just technology. Microservices are driving fundamental changes in how organizations structure technology teams and manage software development processes. They foster truly autonomous teams, which can experiment more rapidly, iterate on ideas with less friction, and ultimately drive continuous innovation. This agility also enables entirely new business models, such as API monetization, where a company's internal services can be exposed as products themselves, creating new revenue streams.
Selling access to their services.
Potentially, yes. It's about building an adaptable, resilient, and future-proof organization that can thrive in an increasingly digital-first world.
Okay, so for an organization that's considering embarking on this journey, or perhaps one that's just starting to dip its toes in, how do they actually begin? What's the practical step-by-step path forward for successfully implementing microservices?
Right. It's definitely not something you jump into lightly or without considerable preparation. The very first step is always thorough assessment and planning. You need to evaluate your organizational readiness across several dimensions. This means looking at your existing system's complexity. Is your current monolith a tangled ball of spaghetti code? Or is it relatively modular? Identify existing performance bottlenecks, chronic development challenges, assess your technical debt. This comprehensive understanding sets the baseline for your transformation goals.
So really understanding exactly where you are before deciding where you need to go. What else needs to be rigorously assessed?
You also need a thorough team and skills evaluation. Assess your current DevOps maturity. How good are you at automation, CI/CD, operating software in production? Do your teams possess the necessary expertise in distributed systems design, containerization, cloud-native tech, or do they need training? How are your teams currently structured? Microservices almost certainly require organizational changes here, as we discussed with Conway's Law. And finally, an infrastructure assessment. Review your existing cloud readiness, your current monitoring and observability capabilities, your existing security frameworks. Do you have the underlying foundation and tooling to support a complex, distributed system? This upfront, honest work is invaluable.
Once you've assessed your current state and capabilities, what are the non-negotiable prerequisites for success? What absolutely has to be in place before you truly commit to a microservices migration?
There are critical, technical, and organizational prerequisites that, if not addressed, will significantly derail your efforts. On the technical side, you need deep Docker expertise within your teams for containerization, a robust container registry for storing and managing your service images, integrated security scanning for those images from the start.
Security built in.
Absolutely. Kubernetes proficiency is pretty much essential for effective orchestration at scale these days. Automated CI/CD pipelines are non-negotiable for continuous integration and deployment. And finally, comprehensive monitoring capabilities. Remember, if you can't see what's happening, you're flying blind in a distributed system.
And what about the people and processes side? That seems just as critical based on what you've said.
It's arguably more critical sometimes. Organizationally, you need to foster cross-functional teams. Teams that have all the necessary skills development, operations, QA to build, deploy, and run their specific service end-to-end. There must be clear service ownership where teams fully own their services, embracing that you build it, you run it philosophy. A strong DevOps mindset is crucial, embedding shared responsibility for operations and automation across teams. You need a culture with a healthy failure tolerance, understanding that in distributed systems, things will fail occasionally, and the system needs to recover gracefully. It's not about preventing all failure, but managing it.
Designing for failure.
Exactly. And finally, a strong continuous learning culture to keep up with the evolving complexities and new technologies in this space. Without these cultural shifts, the technical adoption will really struggle.
That sounds like a significant undertaking, combining technical mastery with profound organizational change. Is there a typical roadmap for how this transformation unfolds, and what kind of timeline are we looking at for a successful migration?
There is indeed a typical phased approach, yeah. And it's important to understand this isn't a quick sprint. For a significant migration, you're generally looking at a timeline of around 9–12 months, often longer for very large enterprises or complex systems. Phase 1, foundation building, months 1 to 3. This is about establishing your core infrastructure. Get your Kubernetes environment deployed, set up foundational CI/CD pipelines, implement robust monitoring and logging solutions, and begin training your teams. Crucially, you select a small, non-critical pilot service, one with minimal dependencies, and extract it from your existing monolith using that strangler fig pattern.
Start small, learn fast.
Precisely. This allows you to learn iteratively, iron out processes, build confidence, and validate your assumptions on a smaller, lower-risk scale without disrupting your core business.
So start small, learn from it, and build that crucial internal muscle. What's next after the foundation is securely laid?
Then comes Phase 2, core services migration. Months 4–8. This is where you begin serious service decomposition. You systematically break down more core functionalities into microservices, rigorously applying domain-driven design principles to define clear boundaries. You also tackle data store decomposition, ensuring each new microservice has its own independent database. That can be tricky. You establish sophisticated inter-service communication patterns, maybe enhance your platform with tools like a service mesh for improved traffic management and security. Further improve your distributed tracing and observability. This phase also involves scaling your teams and potentially restructuring them further as you introduce more services and solidify ownership.
And finally, once the core functionalities are largely migrated, what's the last phase about? Is it just maintenance then?
Not at all. Phase 3. Advanced capabilities and operational excellence, months 9–12. This is about achieving true operational mastery and maximizing business value. You implement advanced deployment patterns like blue-green deployments running 2 identical environments, one live, one new, for instant, risk-free cutovers. Or canary deployments, gradually rolling out new code to a small percentage of users first.
Testing the waters.
Exactly. You introduce chaos engineering, intentionally injecting controlled failures into your system to proactively test its resilience under stress, a concept pioneered by Netflix. And critically, you focus on business value realization. Continuously measuring key business metrics, leveraging feature flagging to control the rollout and A/B testing of new features. It's about optimizing, hardening, and proving the value.
Those are clear, actionable steps. But what are the absolute critical success factors to ensure this entire roadmap goes smoothly and delivers the promised benefits?
4 factors stand out as absolutely critical. First, automation. As we've emphasized repeatedly, heavy ongoing investment in CI/CD, infrastructure as code, monitoring automation is non-negotiable. You cannot manually manage this complexity. Second, observability investment. Prioritize comprehensive observability, distributed tracing, centralized logging, granular business metrics from day one. If you can't see it, you can't fix it. Third, security integration. Security needs to be secure by design, baked into every service from the ground up. Automated security scanning and pipelines, zero trust networking principles. It is not an afterthought. And fourth, leadership commitment. This transformation requires sustained, visible leadership support for the investment in tooling, team transformation, cultural change. And perhaps the most important underlying principle wrapping all this up is an incremental approach. Always start small, learn iteratively, and validate assumptions with pilot projects. Do not attempt a big bang full rewrite. It's almost always a recipe for disaster.
That's invaluable advice. And speaking of pitfalls, what are the most common traps or anti-patterns that organizations fall into when attempting microservices, even with the best intentions?
The most common pitfalls, number 1, is probably creating a distributed monolith.
A distributed monolith, how does that happen?
It happens when you've broken an application into many services, but they remain tightly coupled. In terms of data sharing, synchronous calls everywhere, deployment dependencies, you end up with all the operational complexity and network latency of a distributed system, but none of the promised benefits of independence and agility.
All the pain, none of the gain.
Pretty much. You avoid this by rigorously enforcing clear service boundaries, ensuring independent data stores, and favoring asynchronous communication where possible. Another big one is inadequate monitoring. Insufficient observability creates operational blind spots, making it incredibly hard to troubleshoot and understand system behavior, especially under stress or during failures. Address this with comprehensive instrumentation, clearly defined business metrics, proactive alerting, don't skimp on observability. And finally, as we stressed, the Big Bang migration, attempting a full rewrite of your entire legacy system all at once. Extremely high risk, often leads to spiraling costs, missed deadlines, and ultimately, project failure. The incremental strangler fig approach is almost always the safer and more successful bet. #tag. Conclusions and strategic recommendations.
What an incredible deep dive. We've journeyed from defining microservices and understanding its transformative potential to exploring its historical roots, diving deep into its complex technical components, examining its immense industry impact, weighing its merits against monolithic architectures, and finally, understanding the formidable challenges and the practical, proven steps to overcome them. It's abundantly clear that this is not just a technical shift, but a fundamental paradigm shift for software development. So, what are the ultimate key takeaways from all this? And what are the strategic recommendations for organizations and individuals navigating this landscape?
Yeah, the overarching takeaway is crystal clear. Microservices architecture is not just some passing trend or an experimental concept anymore. It is a mature technology paradigm that has fundamentally transformed modern software development. The numbers really speak for themselves. 85% of modern enterprise companies are now leveraging it for complex applications, and a compelling 74% of organizations are actively using this architectural approach. This widespread adoption isn't just accidental.
That's a truly massive shift in a relatively short period, cementing its place as the standard for many.
Indeed. The validated benefits are substantial and quantitative. We have robust evidence supporting that 53% faster time to market for new features and a 41% increase in overall development productivity. These aren't minor improvements. They directly translate to profound competitive advantages and accelerate business innovation. The continued market momentum also tells a story of sustained confidence, with projected continued growth indicating ongoing enterprise investment and a belief in its long-term value. This reflects the deep maturity of the ecosystem. It's moved decisively beyond experimental to mainstream implementation, with established patterns, tools, and best practices readily available.
So for many organizations, it's probably not a question of if they should adopt microservices, but how and when. What are the strategic recommendations for different leadership levels within an organization as they consider or deepen their microservices journey? Let's start at the top with the executives.
For executives, the recommendation is to prioritize microservices as a strategic investment for long-term growth and innovation. While there's an acknowledgement of a potential 50–100% increase in infrastructure costs, initially due to the distributed nature and orchestration needs a strong ROI potential, with 87% of companies reporting justified expenses, often makes it a worthwhile investment.
Cost versus benefit.
Exactly. The key here is to embrace gradual, incremental adoption strategies. Focus on learning and adapting iteratively rather than attempting risky, all-at-once transformations. This needs to be seen as a strategic business decision, not just an IT project delegated downwards.
And for the technical leaders and architects, the people on the ground making these crucial design and implementation decisions.
For technical leaders and architects, the recommendation is to adopt domain-driven design principles from the outset. Define clear, cohesive service boundaries. Actively prevent the emergence of that distributed monolith anti-pattern. Prioritize an API-first design with robust governance. Firmly establish a comprehensive observability foundation, detailed monitoring, centralized logging, distributed tracing before scaling up your microservices fleet. Security also needs to be deeply embedded throughout the entire software development lifecycle, not treated as an afterthought. And critically, invest strategically in foundational technologies like Kubernetes and service mesh technologies such as Istio. These are really the backbone of large-scale, resilient microservices deployments today.
And for the development teams themselves, the engineers who are building and running these services every single day.
For development teams, the focus needs to be on continuous skill development in areas like containers, advanced distributed systems patterns, cloud-native platforms. It's a new way of thinking about software that requires a different skill set. They should also fully embrace the you build it, you run it responsibility. Teams are truly accountable for their service throughout its entire life cycle, from development right through to production operation.
Full ownership.
Full ownership. And finally, implement comprehensive testing strategies that are specifically appropriate for distributed systems, to including integration tests across services, contract testing, and resilience testing like chaos engineering.
So, to summarize the overall implementation priorities, how should organizations best phase their approach to ensure success and mitigate risk?
The typical phased approach begins with phase 1, foundation building. Establish your core Kubernetes environment, set up robust CI/CD pipelines, implement foundational observability tools, and crucially, start the reorganization of teams around clear service ownership. Pilot project here. Then, in phase 2, core migration, you systematically decompose more core services and their associated data stores, implement enhanced security measures, and optimize for performance based on learnings from phase 1. Finally, phase 3. Advanced operations and optimization is about achieving true operational excellence, implementing advanced deployment patterns like blue-green and canary releases, leveraging chaos engineering, and continuously focusing on measuring and demonstrating the realized business value.
What an incredible deep dive into microservices architecture. We've seen how this isn't just a technical shift, but truly a profound strategic one, enabling unprecedented speed, scale, and resilience for some of the world's biggest and most demanding companies. From how Netflix streams movies to how Amazon delivers your packages, the way you experience software is being fundamentally redefined by this.
Indeed. And while it absolutely introduces its own set of inherent complexities and challenges, it's not easy the quantifiable benefits. In terms of dramatically faster time to market, significant reductions in development costs over the long term, vastly improved system resilience, they're truly compelling for many businesses. It's a powerful testament to that timeless principle of breaking down large, unwieldy problems into smaller, more manageable pieces, and fostering true autonomy and ownership at every level of an organization.
So what does this all mean for you, the learner, beyond the fascinating technical details?
Yeah.
It highlights a broader fundamental principle, the immense power of modularity, independent teams, and decentralized decision-making to drive continuous innovation and adaptability. It also means you, as an end user, can probably expect the software and digital services you rely on to become even more robust, responsive, and innovative over time, constantly improving, hopefully without disruptive downtime.
And this raises an important question for you to consider, perhaps one that extends beyond the realm of software entirely. How might the core principles of microservices, things like fostering independent teams with clear responsibilities, designing for fault isolation, embracing incremental adoption, how might those apply not just to complex software systems, but to other large, complex projects or organizational challenges you might encounter in your own work or even your life?
That's a truly thought-provoking question to mull over. Thank you for joining us on this deep dive into microservices architecture. We hope this comprehensive exploration has given you a profound shortcut to being well-informed about this critical topic, and perhaps sparked some new ideas about problem solving in an increasingly complex and interconnected world. Until next time.